put down another tornado. So that's a little bit about some of the things that we're trying as far as the art is going. The second part of this false alarm problem is about the science. Science is tougher because it's longer time. You know, you got to spend a lot of time rooting through the data, collecting data. Results are always going to be inconclusive with science. It's going to be frustrating at times. So, but you definitely want to take a look at it. In other words, you want to incorporate science of tornado warnings into the warnings. That makes sense. So I want to step back and take a look at what we've done. I went back through the polygon warning error, which again is October 2007 through present. And these are the kind of numbers that we're looking at. QLCS, 82 total tornadoes, supercells, 128. We even had some tropical in there as well. The interesting thing here is that minus April of 2011 and QLCS tornadoes are about on par with supercell. And yeah, there's a lot of rhetoric about how to handle QLCS tornadoes and specifically, and they're usually the weaker kind. And I suppose some of that is true, but supercells are weaker as well. I mean, honestly, taking a look at F4s and F5s, we've only had 5 total. Obviously, we haven't had any for QLCS, but you know, that's not a lot of disparity between. I mean, like I said, most tornadoes are going to be zeros, ones, and maybe some twos in there. So that's just something to keep in mind. How about the unwarned tornadoes? We've had 50 of them in 5 years and 1 month. Most of those have been QLCSs, 14 to 29. So we've pretty much doubled on the unwarned tornadoes with QLCSs versus supercell. We've also had some unwarned tropicals as well. We've had 1 fatality from a QLCS tornado that was back in May 2008. So we have had that 1 fatality from unwarned, and it did come from a QLCS. Okay, taking a closer look at some of these numbers here is the count again: QLCS, supercell, and tropical. Okay, tornadoes with a warning. Okay, so a little bit of disparity there, 53 to 82 for that QLCS. I think we need to do some improvement there. But what about the warnings themselves? And they jump way up. So you can kind of get a sense of what the false alarm rates really look like per mode of convection here. The FAR didn't have as much disparity as I thought. You know, the way you hear the rhetoric going around about QLCS is you think it's probably double the false alarm. Not really. 13 points. So it's still high on all counts. One thing that surprised me was the tropical false alarm rate, way up there, 91%. So it's almost like you don't ever hear anything about tropical tornadoes. It's almost like if you take those away, the numbers just get better by 10 points just by eliminating tropical. But you know, sometimes that gets kind of swiped under the rug there. How about the POD for each one? A little bit more disparity there between QLCS and supercell. So we've got our work cut out for us, really, on all 3 counts, to be totally honest with you. The POD for tropical was horrible too. It's 53%. Lead times I don't have any problem with. I liked all the lead times we had, especially that supercell lead time. That's good, 27 minutes. I mean, we're pretty much beating the mandate on average overall. So even 12 minutes for the little QLCS spin-ups is pretty doggone good. So don't have a lot of issues with lead time at all. Looking at some QLCSs, and that's really where we started because that was getting the most attention at the time, is what to do about QLCSs. So that's where the research led us to begin with, and we took a look at all of these events one by one. There's some interesting things that come up, and again, we looked at a lot of events. We've had around 119, I think, events, so I kind of cherry-picked some of these. And you can see, especially on the QLCS front, going back, especially December 10th, 2008, 20 QLCS warnings here. This is event number 21, with a 90% false alarm rate. Okay. A few months later, here's another 28 warnings. 28 warnings with a 96% false alarm rate. Okay, I think this event had 2 tornadoes, one of which didn't even have a warning with it. The next event, May 6th, 13 more. Didn't do too bad here, 56, but we had 4 unwarned tornadoes. So in other words, we got a lot of work cut out for us. And the supercell as well. How about October 26, 20 supercell warnings, 100% false alarm rate. The one tornado we did have didn't get caught in one of the 20 warnings, so the POD was 0. Okay. Same thing leading up to April of 2011, April 15th, and then April 27th. You had this event here at March 26th with 21 warnings. I think we had 1 tornado. So that led to a 95% false alarm rate. We did get it, but it's still, we had 20 warnings that went without a tornado. And then the biggie was probably April 11th. This was a total QLCS event where we put out 11 warnings. I think it was like a Tuesday night. We put out 11 warnings with a 91% false alarm rate. Yeah, it was 100% POD. We had the 1 tornado, but all the other ones had a false alarm. So I think this really led up to the culmination of people being frustrated with the overwarning problem. So we did have our work cut out for us. So I said to myself, well, okay, can we look at any environmental parameters with QLCS that may lead to improved warnings? So we looked at 20 events. We looked at the top 10, and then we looked at the bottom 10. So 10 QLCSs that didn't produce, 10 that did, or our heavy producers. We tried to get as much disparity as we could between the two groups. Okay, then we broke that down further and looked at some cold season events, say, versus warm season. Our cold season is basically going to be November through February. And what we looked at was we wanted to stick with things that people know. So if you look at SPC's page, mesoanalysis page, that's what you're going to find. We looked at 39 total parameters, and SPC does use a lot of RUC data, at least at the time they did. So we looked at 39 total parameters, and we looked at temporal stuff as well. So we went 6 hours before the first warnings through 6 hours after the first warning. So we tried to get some trends as well. Ended up being about 19,000 data points, which, you know, that's pretty significant. So I was pretty happy with the data gathering part of this. What do we find? Well, let's go to the go-to products. Everybody loves this 0 to 1 kilometer storm relative helicity. All right. And what we found is interesting, especially in the cold season there. Notice that in the cold season that as the shear goes up, the higher helicity, you actually turn into non-producers. So in other words, it looks like in the cold season, in the dead of winter, the more shear you have, the worse it's going to be for you actually getting a tornado. Exactly opposite in the warm season. So the more shear you have in the warm season, the better it's going to get. And these colored boxes is the 25th through 75th percentile. So it's about the, you know, the on average, this is what you would expect. All right. I just found it really interesting because one goal of this research is to break down this paradigm of what we've always thought, and that is more shear equals more tornadoes. So if you come in and you're seeing helicity values 0 to 1 jump up 300, 400, 500, even getting close to 600, you're thinking to yourself, oh, this is going to be a big tornado day because we have a lot of shear. Well, it turns out that may not be the case, especially in the dead of winter. So not a bad finding there at all. Okay, 0 to 3, same kind of stuff. They're obviously related, but you get this huge jump up when you get these non-producing events, 0 to 3. Opposite in the warm season. So it jumps up in the warm season. It looks like you need more shear. How about the next big go-to product is this surface-based CAPE. Turns out CAPE is, especially in the warm season, not a very good predictor of anything. Look how big these error bars or 0 to 100 percentiles are for warm non-producers and the warm season producers. So in other words, we've had events, non-producers, 0 to over 2,500. So the more CAPE didn't mean anything. Same thing with the warm producers as well. We've had 100 to, say, 2,000 joules per kilogram, and they end up being producers. So in other words, these two overlap significantly here. Doesn't really tell you anything. Cold season, I thought it did a little bit better job. So in other words, if you're down in this 2 to 300 range in the cold season, it looks like not much is happening. You really need to jump it up to about 3 to 700. So just a little bit of CAPE will be enough in the cold season to get the producers going. So there's a little bit of disparity there. So think about that next time we're in the winter season situation. MU cape, which is directly tied, it's the most unstable cape, directly tied to surface-based cape, sort of the same thing. Not a lot of disparity in the warm season. Cold season, you definitely get that uptick from non-producers to producers. So definitely some things to learn there, I think. LCL, liquid condensation level. This one's very interesting to me because a lot of time LCL refers to supercells. Never heard it in context of QLCSs, but take a look. Not a lot of traction in the cold season, but the warm season you get this huge thing. So in other words, the LCL, the lower it is, and this is in meters, so it's 600 meters or less, it looks like you get a lot of production. If it gets above that, 650 higher, we're not getting any producers. So definitely in the warm season, definitely something to take a close look at as we go through, but you just don't hear a lot of things about the liquid condensation levels associated with squall lines. It just doesn't seem to come up that much, and turns out we may have been missing it all along here. And then we got to something that I found very interesting, the highly correlated line orientation. This ended up being the most correlated parameter of anything we looked at, all 39. And I found it interesting because I never thought to think about what line orientation did to the squall line. Okay, so we have this squall line here that's oriented, I have 0 to 180. In other words, it's almost north-south. Okay, standing straight up and down. Say versus one that's leaned over even a little bit. I call this one 30 degrees to 210. So turns out the further oriented northeast to southwest it is, the less likely it is to produce. So in other words, if it's standing straight up and down, north to south, expect a lot of tornadoes. The further it's leaned over, expect less amount of activity tornado-wise. Okay, I tried to put it on this line graph here. So in other words, at 180 right here is when the storm is standing straight up and down. And look, between 170 and 190, when it's almost north-south, is all of our red producers. Okay, when it's tilted over, as we get to more like 210 to 250, getting closer to east-west orientation, it really drops off big time. Okay. Now, I will be the first to admit this is only 10 events. Okay, so I don't have a lot of answers, but why there is no mix at all. Okay, there's a definite changeover once you get to a certain angle. We plotted on our little bar graphs, and another thing that came up, and that is it only worked in the warm season. I can't explain to you why in the cold season it didn't seem to work. I want to study that a little bit further, but for now, warm producers have this 180 to 190 orientation. So in other words, they're basically 0 to 180 or 10 degrees to 190. They're standing straight up and down. And the further it's leaned over, you start to get into this non-producers. But look, there's a huge gap in between these two. So I think there's probably some scientific credibility to this, and this is definitely going to be something that we look at in the future. This hasn't been tested out in live, real-world stuff yet. This is all looking at historical data. Quite interesting to see this line orientation stuff. Didn't make a lot of sense to me. So I went back and I started thinking about it. And by the way, this is 93% correlate. That's incredible. That's a very high correlation. But I started thinking about it. I was like, it can't be line orientation. Something else has to be going on. And it turns out it's this 0 to 8 kilometer shear vector. And I don't know anybody in the research papers or anywhere else who look at the 0 to 8 kilometer shear vector for QLCSs. It's unheard of. Most people are thinking about 0 to 1, 0 to 3 kilometer kind of stuff, the lower boundary layer. I've never thought to look deep in the layer to see if there's something else, and indeed there is. Turns out that this vector, if it's blowing into the back of a line at 90 degrees, and I don't care how the line is oriented, okay, if it's oriented east-west and this vector is blowing into the back of it from the straight north, in other words, as long as this angle in between the line and the vector is at 90 degrees, you're in good shape. So, in other words, once you get to about, really the cutoff was about 45 and higher as you get up in the 90s. See, my angle is over here on the side. So once we get to a certain place, it turns red, and these become producers. Okay. If the line is oriented more toward like 20 degrees or more parallel to the QLCS or the squall line, the closer it is to 0 becomes a non-producer. So what I wrote, 0 to 8 kilometer shear orientation blowing 90 degrees behind the line is much more favorable for tornadoes during the warm season. Remember, this only applies to the warm season. So in other words, the more at a right angle it becomes, or 90 degrees, the better chance it is for a producer. Didn't have a lot of explanation for that other than the fact that probably the winds blowing into the back of the storms allows for updraft separation. So in other words, it still looks like on radar like a squall line, but the winds are actually allowing the updrafts to kind of separate, and once you get that separated updraft, the storms become much more dangerous. And from a radar perspective, it's very hard to pick this out, but I think that's exactly what is happening with these storms. So in other words, you start to see these little kinks like this all over the place because of the way the shear vector is lined up compared to the squall line itself. Very interesting. So we plotted that one out as well. So this is, again, it's not the 0 to 8 kilometer bulk shear, it's the orientation it is to the line itself. So the higher, the more the angle comes like 90 degrees, you're definitely getting these producers. And when it's more parallel to the line itself, you're getting these warm non-producers. Cold season, it just didn't seem to work out. I want to study this a lot further and see if it'll take us anywhere as we get more events under our belt. All right, so that's what we kind of looked at with QLCSs. I think we're getting somewhere. Okay, I didn't think that was enough. I thought we needed to look at everything. Let's throw everything into a pot. Tropical, supercell, and QLCS. And we looked at total events 119, and we went back to 2005. Why did we stop there? Well, that's basically where SPC and their little meso-analysis, that's where the database kind of stops at about 2005. Late 2005 at that. So we have 119 events. This covered 259 tornadoes, and the total warnings were 841 over the same time frame. So this is kind of what we got out of it. First of all, the disparity between different tornado types. You hear about this and you kind of wonder maybe what it is for our area. Here it is. F0s and F1s certainly dominate. Quite a few F2s and F3s for just a 7-year period. But certainly the disparity is on that smaller end, as you would expect, the F0s and F1s. Okay, the first parameter we compared all these events to were surface-based K. Okay, how do they compare? Okay, this is the number of tornadoes in percentage over on the left-hand side. And it turns out that CAPE is pretty much worthless when it comes to tornado occurrence. Believe it or not, 80% of our tornadoes come with surface-based CAPE 1,000 or less. 80%. Okay? And when you go from 1,000 to 2,000, you only jump up about 10%. So you go from 79.9 to 91.9 just by adding another 1,000 joules per kilogram. So what is this really saying? It's saying if you're depending and looking at CAPE, surface-based CAPE, as your distinctive parameter for tornadoes, you can forget it. It's not going to happen. We have a lot of tornadoes in the 500 range. We have a lot in the 1,000, and we actually have less as you get higher, just in general. Okay. So I've overlaid the number of F0 and F1 tornadoes, and again, most of those fall from about 1,200 or less. Well, you think, well, okay, stronger tornadoes. Not true. Same thing with the F2s and greater. Look, we've had a lot of F2 or greater tornadoes with 1,000 or less. Okay, there's a significant bump out here at 2,500, and this is all due to April 27th. That one day has allowed for this significant bump out here at the end. Okay, take away that day, and this bump pretty much goes away. So all of our tornadoes basically lie from about 1,200 joules per kilogram or less. So in other words, if you get enough CAPE, if it's not 0, and you're starting to get around oh, 300, 500, especially in the 700 range, you can forget it. Cape is good. You don't need to worry about instability. You're good to go here. Kind of a funny thing, too, is that April 27th, we talk about that a lot, 2500 Cape. April 15th, we had a major outbreak here, too, that gets looked over a lot. 31 tornadoes. 31 tornadoes on April 15th. What was the Cape on April 15th? 700. Okay? So that's probably where this bump comes from. 700 Cape on April 15th with 31 tornadoes. So you absolutely have no chance by looking at Cape. As long as you have enough, 300, 400, 500 or more, you're good to go. Don't worry about it anymore. Okay? Moving along. 0 to 1 kilometer shear. Now this is not helicity. This is the shear vector. What is the magnitude here? A lot better disparity with it. So it's looking like once you get over 30 knots, you're good to go. Question is, what happens below 30 knots? Well, only 16% of our tornadoes have been 30 or less. Okay? If you have 20, it's 2.3% of our tornadoes. Okay? So it's looking like if you get anything over 30, get into the 35 range, you're good to go there as well. Okay? Overlay the tornadoes with that, much as expected. Okay? The significant percentage really starts at about 30 or 10%. And these are all the weak tornadoes, and it really goes up from there. Same thing with the number of greater than EF2 tornadoes. So it's looking like independently in any way that 30 knots is going to be a nice little cutoff. Anything less than that, you're getting into the less than 10% range. So I got interested, and I thought, well, this may be where we can start to improve some in these lower numbers. So I've changed the graph a little bit. It's the same exact line of the 0 to 1 kilometer shear in knots, but I've put the number of tornadoes we've actually had, not the percentage, at each dot. So in other words, 42 of our tornadoes have come with 30 or less. You get down here to 15 knots, and we haven't had any historically. Now I want to overlay the number of warnings on the same chart. So this started to tell me a big part of the story. Okay, so with 30 knots, we've had 42 tornadoes, but 268 warnings. Come down here to 15, where we've had 0 tornadoes, but we've issued 25 warnings. 26, but we've issued 59 warnings. So what I'm saying to myself is, okay, if you walk in and we're putting together a game plan of how we want to handle this event, and the shear is only 20 knots, 0 to 1, I can say to myself, historically, out of 259 tornadoes, we've only had 6 in our history with 20 knots. So, and we've had nearly 60 warnings. So we can back off just a little bit. Same goes for 25 and even 30. So what I'm trying to say is, in between these two lines, there's some significant improvement that probably should be going on here if we have this historical perspective under our belt. Okay, you walk in here, and this is something that you can look at on SPC's page. If you see that there's 30 knots of shear, historically we've only had 42 tornadoes, but a 268 warnings. I'm saying maybe we can just ease off the trigger finger a little bit with the issuing so many warnings if we know this number is on the lower end, which a lot of times it is on the lower end. Now, once it gets up near 40, 50, it's a whole different ballgame. Things change dramatically. But 30 or less, I think we can start to look at some things a little bit more carefully before issuing a lot of warnings. How about LCL? And again, we looked at about 39 parameters, and I've only picked out 3 here. LCL, very interesting as well. Huge disparity. Percentage of tornadoes really takes a major jump at 800 meters or less. So now LCL gets 800 meters or less, big time jump. So at 900, you're talking about 10% of all of our tornadoes have occurred at 900 or above or higher LCL. It's almost like if you get into the quadruple digits, 1,000, especially 1,100, you can almost forget it. You walk in today and the LCL is 1,400, there is no way you're going to get tornadoes out of that, according to the data that we looked at historically here. Take a look at the tornadoes associated with it. The weaker ones are all down in that range, especially 1,000 or lower. The stronger tornadoes, same kind of deal. Big spike there at about 700. So you're really looking at about 900 or so or less. Really gets going about 800 to 750. Gets below that, you're good to go. Okay? So I did the same thing with the warning. So I've actually put the tornadoes down here. Okay? We've had 3 total tornadoes when it's 1,100 or higher LCL. Only 14 when it's 1,000. How many warnings? The same numbers. Okay? And this is, I think we can really do some significant improvements. Okay? 1,200 LCL, we've had 3 tornadoes, 46 warnings. Same thing with 1,100, 3 and 48, 1,000 even. 14 total tornadoes with 1,000 or higher, 139 warnings. 900, same thing. Huge jump here, and I think we can work to bring this down. So, hey, you walk in, it's 1,000. Historically, we don't have that many tornadoes with 1,000, less than 10%. So we need to bring that 139 down. I think that's where we can start to make some significant improvements. Okay, so what I went back and did was ran all the numbers from 2007, the polygon warning error, through 2011, and it looks like our numbers are about Weather Service average. POD 76%, FAR way up there 80%, lead time 17.5. And remember at the beginning of the show I said that the hypothesis is that if you try to bring down the false alarm, that you're also going to harm your POD and lead time. So now that we've started to implement some of these techniques I've described to you, which has been this year, we're starting to see some results. The PODs are up to 92%, and I've really been impressed with the false alarm decrease. We've decreased it by half this year. And we didn't hurt the lead time either. 17, it's actually gone up just a tick. So I've been pretty impressed so far with these preliminary results. And again, we got a lot of work to do. We got a lot of work to study. We haven't even begun to look at the radar yet. So there's certainly going to be something probably to the radar data looking at it as well. But just with the techniques I've described, and especially with this environmental stuff, we're already starting to see some positive results. So I think we're going to continue in that direction. And these numbers at 2012, these are the kind of numbers I can live with. I can live with a false alarm rate that's 40. I think we can still do a little bit better beyond that, but it's certainly a significant improvement from what we've had. All right, so with that, I will take your questions.